simulation. So it's a great pleasure to introduce Michel Mandjes, who is going to speak to us on simulation-based computation of the workload correlation function in a Lévy-driven queue. Michel has numerous awards in this area. He's actually, your MS thesis was awarded a Dutch research prize on large deviations, and his work on rare event simulation received the Marcel Nutz Award in 1999. There's a 2007 monograph well aware of on large deviations for Gaussian-driven queues. And he will learn more about these topics. So thank you.
Well, thanks very much, Sean, for this very nice introduction. Yeah, I know it's early for you. But let's therefore start with the bottom line. And the bottom line is that there are more urgent things in life than math, and you know about that. And in order to give you some more feeling for that, I can tell you a little bit more about what happened. Well, let me start with a number of truths. So it's true that Brazil won the World Cup 5 times. But Holland should have won the World Cup at least 5 times. Let me say a bit more about it. Let me see whether you know your classics. What went wrong? Well, a lot went wrong. 1974, well, there are a number of older guys in the audience who may know about this team. So they played on a beautiful afternoon in July 1974 against Germany, the finals of the World Cup. They were better, of course they were better, but they lost. So a lot went wrong there. 4 years later, again Holland made it to the final, again against the home country, Argentina. What went wrong? Last minute, you see that guy over here, Rob Rensenbrink, hitting the post in the last minute, otherwise we would have been world champion. Then you got the dark age of Dutch football, so that lasted for like 12 years, and then we were back, 1990. We had just become European champions, so everybody was optimistic. And then we went to Italy to win the World Cup. Everybody was in the right mood. And what happened? Everything went wrong. Look at this. Well, it's hard to see maybe, but there is something white over there, and that is not what should be there. So everything went wrong there. 4 years later in the US, of course we should have won. There was a quarterfinal against Brazil. Look at this. So this wall of players skillfully protecting their vital parts. And there is here Mr. Branco shooting in the corner. So we were out. Bad luck. 4 years later, we made it to the semifinals. That was nice too. There was a beautiful goal of Dennis Bergkamp, but then there was a penalty shootout against Brazil in the semifinals. So we were out again. And then we were optimistic because we had a new coach, and that was a very strong guy. You may know him, Louis van Gaal. He promised us to make us twice world champion, and what happened? We didn't even survive the qualifications, so we never made it to Japan nor Korea. So our German neighbors were very happy about that, so they had a funny website about that. I won't tell more about that. And then there was 4 years ago the very embarrassing game against Portugal with 17, believe it or not, yellow cards and 2 red cards, of which you see one over here. So I hope this is enough evidence that we should have been world champion many times, at least more than the Brazilians. More embarrassing news. It's only my second racing workshop that I attend. The first time I was there a long time ago in Aachen, but after that, for some reason, I never went there, although it was held in beautiful cities like Pisa and Budapest, Enschede, but I never made it to to RESIM. And then the last thing before I really start is an advertisement. Bruno was very modest yesterday. He didn't even mention the book that he wrote together with Gerardo. I think it's a very good read, so I really advise. Well, it's a very nice thing to have. It's really a must if you work in this field. It's a very nice survey, so pay attention. Okay, let me start with the talk. So far during this workshop we have been looking almost exclusively at things like rare event probabilities. So there is an event that is rare and you want to find out how rare it is. But this talk focuses on something else. It focuses on moments that vanish in a certain parameter. So the leading example that you should have in mind is that you look at a queue, you look at the workload of a queue and you observe it at time 0 and at time t, and you let t grow large. Of course, the correlation between the two workloads will vanish, but we want to know at what rate that vanishes. Are there rare event simulation methods that we can use there? So it's a completely different problem. You will notice that all the things that we are used to break down in this case. So all the things that we developed over the past years are not applicable there. We will do so in the context of Lévy-driven queues. So don't be afraid, I'll explain in detail what Lévy-driven queues are. But let me first say a few words about queues in continuous time, because you are used to, well, the kind of Lindley type of equations of this type. So that is something that we saw yesterday and the day before yesterday several times. The queue at time n plus 1 is something like the queue at time n plus an increment, can be positive, can be negative. And if the whole thing becomes negative, of course you truncate it at 0. So that is the famous Lindley equation. You can iterate that one, and if you do so, then you end up with a formula of this type. So this is something like a queue in, well, let's say discrete time. The interesting thing is that you can talk about its continuous time counterpart in this way. So I just look at a counterpart of this thing in continuous time, and then you get something along these lines. So in this way you have defined the notion of a queue for any input process that you like. So even if this the input process is not increasing, you can talk about a queue in this way. An example is, well, we can talk about a queue fed by Brownian motion in this way. And we also refer to that as reflected Brownian motion. So it's a very nice technique to look at a broader class of input processes than just the traditional, let's say, MG1 type of things. In this talk, I will look at queues with stationary increments, meaning that xt minus s has the same distribution for a given s, irrespective of the position of that window, so irrespective of t. And as long as there is something like a negative drift, then there should be a stationary distribution of this type. Often Qt is called the workload process. So the thing that we are interested in is, what if we feed a queue by a highly correlated input process? So we have something, an input process with a very strong correlation structure, we feed it into a queue, and what happens to that workload process? The main question is there, is the high correlation inherited by the queue? And that is something to think about. Should it be inherited or not? The key question is, suppose your input process is, for instance, long-range dependent. What can be said about this R of t, the covariance between Q0 and Qt? Is that also long-range dependent? And that is, I guess, one of the very interesting questions that is still widely open. There is a conjecture. Suppose that you look at the most famous long-range dependent process there is, fractional Brownian motion, then, well, the input process has a decay of this type, and the conjecture is that also the workload process has a decay of that type, which would mean that the workload process is indeed long-range dependent for h in this interval, because then these are non-summable. So that was not proven yet, and the main difficulty that you face there is that it's not straightforward to write a covariance in terms of things we know how to deal with. So we can't write it as a large deviation probability. Remember, it's the mean of Q0 times Qt minus Q0, the mean of Q0 squared. So other techniques are needed there. Also, in terms of importance sampling, well, the classical importance sampling techniques don't work. So the main question I want to address in this talk is how to efficiently simulate small correlations. I make life a bit easier for myself. I won't look at fractional Brownian motion. That is a very hard process to deal with. I first look at a queue driven by a Lévy process. And a Lévy process is way nicer than FBM for the reason that a Lévy process has stationary and independent increments. That is, in fact, the definition. You can see that as the definition of a Lévy process. Of course, because of this property, the input process is now, well, it has no dependence at all. If you look at two disjoint intervals in time and the amount of traffic that arrives to the queue, then they are independent. So there is no dependence of the input, but the question is, what can be said about the workload process? Is there some dependence that arises because of the, well, the features of the Lévy process? Well, in this talk I will focus on two things. First, I will go through a number of, let's say, structural results about the covariance function. And after that, I will use those to come up with efficient simulation techniques. And then you will notice that it's completely different from the, well, usual rare event probability type of thing. One thing that makes life even more easier is that I look at Lévy processes that have jumps only in one direction. So that is called spectrally one-sided. So what does that mean? Well, a Lévy process is still that stochastic process with independent and identically distributed increments, but the key point that we want to make is that we look at processes with either only positive jumps or only negative jumps. So only positive jumps, you can think of the, well, the compound Poisson process. So your workload increases by some positive amount every now and then you have some depletion. Spectrally negative is exactly the other way around. There, the jumps are downward. Needless to say that Lévy processes are a key object in applied probability. It's one of the, well, more important themes in the field. Some examples. Almost every class of stochastic processes covers Brownian motion as a special case, and that is true here as well. Brownian motion with drift is actually both spectrally positive and spectrally negative because it has no jumps, so it's both. The other one I already mentioned, compound Poisson with drift. So what you have there, non-negative jobs arrive according to a Poisson process with a certain lambda. The jobs are IID samples from some distribution, and what you get is that, well, there's independence of what arrives into disjoint intervals in time, so it's a Lévy process. Well, we had the definition of a queue in continuous time, and we can apply that with, as input, that Lévy process that I just defined, that x of t. So here you have the position of the queue at time t, that is, well, the value of x of t, plus the maximum of q0 and minus mt, where mt was that infimum. So it's exactly the definition that I gave, and that was the counterpart of the discrete time queue. Important, throughout the talk, I will assume that the queue is already in stationarity at time 0. Remember, I want to say something about the correlation between the queue at time 0 and at time t. And what I assume is that it's already in stationarity at time 0. A bit more about those spectrally one-sided cases before I really start. Spectrally positive case is the one in which the jumps are positive. And then one of the key objects is this phi of alpha. The phi captures all the information of the Lévy process. And here I drew a picture of what phi looks like. Phi is convex because of Hölder. And later on we will also need the psi, which is the inverse of the phi.
Sorry, if the jump is heavy tail, can you get long range dependence?
Yeah, but I will say a bit more about it later on.
What's the stationarity required from the Lévy method?
Say it again.
What does the stationarity require of the?
Yeah, so the mean should exist. So the mean should exist. So in terms of the alpha should be between 1 and 2. That's yeah. Okay, the stationary behavior of this Q is well understood. So I said that we would start in stationarity, and we know everything about the stationary behavior because we know the transform of the stationary Q. That is the so-called generalized Pollaczek-Khinchin formula. So that was found by Zolotarev in the late 60s, I believe. From that, we can, of course, compute the mean and the variance by differentiation, plugging in 0, and we get formulas of this type. Special case is Brownian motion, compound Poisson. If you plug in Brownian motion, then it's easy to see that you get an exponential distribution for your workload. Steady state workload is exponential. Spectrally negative case is way easier to deal with in stationarity. There we have the capital phi of beta. I drew it here. That's something of this type. And now it's not a one-to-one function anymore. So if you define the inverse, you have to be careful. So you have to talk about the right inverse. And one important point is this point, beta 0, which is the root of this equation. So this is beta 0. That will play a role later on. So this is the spectrally negative case in which you have only downward jumps. How to find the stationary behavior in this case? Well, it's really easy because it's very easy to see that e to the power beta 0 xt is a martingale for this very definition of beta 0. And then you can do optional sampling, and that gives that the probability of ever exceeding x is 1 over e to the power minus beta 0 times x. And that is really because you hit every level exactly. So because of the negative jumps, well, the first time that you cross level x, you will be exactly at level x. In other words, you get this equation, and then there is a result that says that the supremum of xt over t has the same distribution as the steady state workload. So Jeffrey Collymore mentioned this result already. In other words, we see that that Q is apparently exponentially distributed with parameter beta 0. So you can also compute the mean and the variance, and that's it. So that is the easy case. So now we know everything about the stationary behavior. Now we want to know a bit more about, let's say, the time-dependent behavior, the correlation of the workload. So as I said earlier on, first I want to focus on, let's say, structural results for that correlation function, and after that I will look into fast simulation techniques. Recall the correlation function is defined like this. Sometimes we forget about the denominator because we know it in the spectrally positive, in the spectrally one-sided case. We computed it, and later on we will also use the Laplace transform of this R. And of course this captures all the information about R. So first the result for the spectrally positive case, we could actually compute that Laplace transform of R. It's this wonderful formula in terms of phi and psi. Remember, phi was that Laplace exponent of the input process, psi was the inverse, and once you know them, you can compute this transform. How do you prove that? Well, the key thing is that we know the distribution of the workload at an exponentially distributed time, capital T, given any initial level Q at time 0. So that transform is known. Well, basically it appeared at various places. One of them is that the paper that I mentioned there, but various other forms that are quite similar appeared elsewhere. For instance, already in Prabhu's book long ago. And then you can manipulate with that a little bit. I won't go through the details here. The most important thing is that you observe that through straightforward tricks that always apply to Laplace transforms, you can get the result that you want. Let me move to an example of the example of Brownian motion. You just plug in Brownian motion that had a specific phi and psi that I gave a few slides ago. You can plug them in and you get this formula. And in this case, it's possible to explicitly invert it. And if you do so, you get this formula for the R of t. And here you recognize the distribution function and the density of the standard normal distribution. So in this case, you can compute things explicitly. In general, you can't. In general, it's very hard to say something about it. What did we do? Well, what we did was proving a couple of, let's say, structural properties for this spectrally positive case. What did we prove? We proved that R is positive. Well, that makes sense, I guess. If you look at two disjoint or 2 points in time, then there should be a positive correlation between the two workloads. The other thing we proved is that it's decreasing in t. The farther they are apart, the smaller the correlation is. But we could also prove that it's a convex function. And this was actually already proven by Teun Otz 33 years ago for the MG1 case, relying on the machinery of, let's say, completely monotone functions. I'll say a bit more about it later on. But we looked at a more general class, all the spectrally positive Lévy processes, and it turned out that the proof that Ott came up with, of maybe 10 pages, shrank to maybe a page and a half. And that happens quite often, I guess. When you look at more general things, well, then you have to think about more general ways to do that. You cannot use explicit formulas, and because of that, we came up with a very short proof. What is that machinery of completely monotone functions? Well, think of completely monotone functions as Laplace transforms of positive random variables. Well, I'll demonstrate the approach later on for the case of spectrally negative input. The other thing my student and I did was that we also looked at asymptotics of RT for t large. So that was about a spectrally positive case, but you could do the same in a spectrally negative case. And I'll say a bit more about that now. So what is, how does that work? Well, in order to get expressions there, one class of functions needs to be introduced. That is the so-called, the class of so-called Q-scale functions. So you define WQ as the function of which the Laplace transform is this 1 over phi of beta minus q. Remember, phi of beta was the Laplace exponent in the case of spectrally negative input. So you define it through a transform. And in addition, you also define the z on the basis of the w. And then there is a wonderful theorem found by Martijn Pistorius some 6 years ago, or a bit longer. And with some abuse of notation, it's something like this. It gives the transform with respect to t of the density of, well, position of the workload at time t, given that you start off at time x. So that is kind of the counterpart of that thing that I showed you for the spectrally positive case, where we had a transform after an exponential time. So here you have something similar. Well, then it's quite easy to see that we can compute things of this type after an exponential time with parameter 1 over q. You look at the Laplace transform with respect to x, with respect to that starting point. Well, then you get again the whole machinery of Laplace transforms, and you can play around with it, and you get that the thing over there equals the difference between these two expressions. So that means that we have an expression for this thing in the end. And as a sanity check, what you can do is that you can plug in alpha is 0, and then you get indeed 1, as it should. But the other interesting thing is that you can plug in beta as beta 0. And why is that interesting? Well, remember, beta was the parameter of, well, with which you weigh the distribution at time 0. And we know that in stationarity, the workload was exponentially distributed with this parameter. So if you plug in as a starting distribution, the equilibrium distribution, you should stay there. And that indeed turns out to be true. And that was quite strange to see that irrespective of Q, you see that everything works out well. Well, then it's again a matter of computations in order to find the transform of this workload correlation Remember, that was the object that we were interested in, and for the spectrally negative case, we now characterize that through the transform. So you recognize here a formula with the phi and psi. A corollary, answering your question, in this case, it's always summable. The R of t is always summable. You can plug in q is 0, and then you get the integral, and you get something finite, which is nice. So it's never long-range dependent in the spectrally negative case. And that makes sense, of course, because the jumps, who are potentially dangerous, are downward. That is not true in the spectrally positive case. In the spectrally positive case, the jumps can be upward, and then, well, there may be quite a bit of correlation in the Q. Okay, I promise you to demonstrate that technique of completely monotone functions, and let's do that for this spectrally negative case. We have that R is positive, decreasing, and convex here as well. So remember, I already mentioned that it was true for the spectrally positive case, but it's also true for the spectrally negative case. How does that work? So it's basically the same type of technique that we use for the spectrally positive case. So the first thing that we do is that we come up with the transforms not of R, but of R prime and R double prime. The way to get them is, well, you just apply integration by parts. There's nothing to that. Okay, then you have the transform of R double prime. Then the magic starts. Later on, I will show that psi 0 over psi q is a completely monotone function. In other words, it's the transform of a positive random variable. Well, this is just, well, basically a kind of linear combination of this thing over here. In other words, it's also completely monotone. Because it's completely monotone, it's the transform of a positive random variable. In other words, R double prime is positive. In other words, R is convex. That's it. And then the amazing thing is that you can continue. You can continue. There's one property of completely monotone functions that you have to use then. Suppose that you know that f is completely monotone, then the g that you get in this way, f0 minus fq over q, is also completely monotone. And that makes sense, of course, because you recognize here the Laplace transform of a residual. So this is a Laplace transform. So you have to keep this one in mind. Well, take your fq this, then minus r1 of q is also in C, because that is exactly that form over there. So you get exactly this result that you can apply here. In other words, minus r1q is in C. In other words, r prime is negative. In other words, r is decreasing. And you can do the very same trick again, and then you prove that R is positive. So it's really a three-step procedure. You start with the convexity, and then you get the fact that it's increasing, then you get the fact that it's positive. Okay, so now we have those structural properties, and now we want to say a bit more about simulation. And before I do that, I first look at a similar problem, namely the busy period in a Lévy-driven queue. The findings of, well, the important sampling procedure for the busy period can later be used for that correlation function. So that is the idea. First I have to define what a busy period is. Again, you start in stationarity at time 0, and you wait until the queue is empty. The first time it's empty is tau. And we define P of t as the tail probabilities of tau. Both in the spectrally positive and spectrally negative case, you can again compute the transforms of P. This is the spectrally positive case. I won't go through the details, but you get again something expressed in these phi and psi. The spectrally negative case is a bit easier. You get a formula of this type, and forget about all the details, but you get something explicit out. But one thing is important. Here you see that this tau has indeed the transform psi 0 over psi q, and that was something that I promised you a few slides ago, that I would prove that psi 0 over psi q was completely monotone, and here I proved it. So also in this case you have the transform. What is the striking feature? If you compare the transforms of the busy period and those of the workload correlation, so those of P and those of R, they have the same branching points. So the branching points are, well, basically, well, how far you can go to the, with the argument of the inverse, how far you can go to the left until it becomes not well defined. So if you look at a, let's say, light-tailed regime, then you will see that those branching points are exactly the same. And what does that mean? Well, it actually means that they should have more or less the same tail behavior. The branching point says everything about the tail. So if you think of the spectrally positive case with light tails, then we roughly have a kind of exponential decay. Theta star, remember, is a negative number in this case, and theta star is defined in this way. Zeta is the minimizer of phi. So here you have this picture. Zeta is over here, and the theta is here, right? So that is the definition. And a very similar thing applies to the spectrally negative case. You get that there is decay with decay rates q star, where q star is a negative number. Zeta is the minimizer of capital phi now, and the zeta is over here, or the q is over there, q star. Okay, so what do we observe? In terms of tails, they behave quite similarly. And our idea now is to use this to develop a technique to efficiently estimate the tail probabilities of the busy period, and hopefully we can use elements of that later on. Okay, how would you do that naively? How would you estimate the tail probabilities of the busy period? Well, the naive way would be to look at all kinds of independent runs. You observe whether your busy period has ended at t or not, and if it has not ended, then you have a 1 and otherwise a 0. You take the sample mean. So that would be the naive way to do that. This has appeared already a couple of times before during this conference. How many runs do you need in order to get a certain precision in terms of, well, the width of the confidence interval divided by the thing that you want to estimate? Well, it turns out that the number of runs that you need is roughly in the order of 1 over the probability that you want to estimate. So this is not going to work. That is the idea.
Invert the Laplace transform to get these probabilities.
Yeah, that is another question. We can tell a bit. Yeah, that's a good point. A more clever idea is to not sample under the original measure, but to use important sampling. And what is the first thing that comes to mind when you think of a long busy period? Well, you have to change the measure in such a way that your drift that was negative becomes 0. And that is indeed the right thing to do. So in the interval between 0 and t, the Lévy process is exponentially twisted in such a way that you get a drift 0 that is written down there. But there is another thing that you have to think about, and that other thing is, what do you want to do with the q at time 0? So you can twist that as well. So should you use the original measure, or should you twist it as well? I didn't know that at the beginning. So what I did was I assumed it was twisted with some parameter kappa. In other words, the Laplace transform under the new probability measure is something like that. And then later on I will look for a good value for kappa. So the measure that we get in this way is q kappa. Well, the usual stuff. What is the likelihood? Can we say something about the likelihood? Can we bound the likelihood? Yes, we can. So the first thing is that you have to observe that the L is the product of two likelihoods. One relates to the Lévy process in the interval 0t, and the other one relates to the contribution of twisting the q at time 0. Well, those are kind of the routine calculations, and it's not hard to see that things like that come out, and you get a simulator of this type, as always. Well, that likelihood turns out to be something like that, and Well, the first option that comes to mind is to not twist the Q at time 0 at all. So you choose kappa equal to 0. And then you get a very striking thing that does not work well. So you have that expression over there on the top, and you know that if tau is bigger than t, that you should have that Q0 plus xt is bigger than 0, because otherwise the busy period would have ended. And that gives you a bound on the likelihood, and that's something of this type. In order to get logarithmic efficiency, we should apparently have, here you recognize the square of the thing that you want to estimate. So apparently we should have that this thing is bounded, and then everything works fine, because that thing is bounded, and the only thing that is left is this one, because kappa is 0 over there. So the thing to prove is this, and that turns out to be not always true. So it looks like kappa is 0 does not work. So you get infinite variance even if you don't twist your Q at time 0. The second option is that you twist the Q at time 0 with the same twist as with which you twisted your Lévy process after time 0, so with that zeta, which is positive. And then it's easy to see that you do get logarithmic efficiency. So apparently, that most likely way for this event to happen is such that there was already a bit more traffic in the queue at time 0, and this gives a handle on that. Okay, so now we know how to deal with the tail of the busy period. Our ultimate goal was to say something about how to simulate the correlation function, and that is the last topic. The key question is, can we come up with an efficient simulator in this case? Remember, your R looks like this, so that was that covariance divided by the variance. Of course, we know the mean Q length for the spectrally positive and spectrally negative case, that's mu, so we can plug in mu right from the start. We know the variance. So one very naive way to do it is to look at things of this type. So you estimate your that mixed moment over there by a kind of sample mean. And the thing to have in mind here, that this is a very delicate issue, because these two numbers for t large will be more or less of the same order. But one you know for sure, that mu squared, and the other one you simulate. So it's a very tricky thing to estimate that. So what is, suppose that RT is the thing that you want to estimate. What is your guess about the number of runs that you need there? Is there any one with intuition here? The guys who already heard this story. Is there anybody?
1 over R.
1 over R? Well, thanks, you saved me, because that's not the right answer. It's very remarkable. The variance of the estimator looks like this. And when t grows large, you recognize something of that type. It's a positive thing. And what you conclude is that the number of runs that you need is roughly proportional to 1 over R squared. So it's impossible, I would say, to do that with naive methods. So what is the solution we came up with? Well, that is a coupling technique that applies very well here. So how does that work? The idea we had was that we define, or we write the covariance or the correlation in this way. So there's a Qt and a Qt star. How do you get them? Well, Q and Q star are both stationary versions of the workload process, but Qt star is independent of Q0. And then you see that everything is okay, because the Q star already started in stationarity at time 0. In other words, it's still in stationarity at time t. It's independent of Q0, so the mean of their product is the product of the means. So you see that this is fine. How do you construct it? Well, the way to do it is that you generate Q0 and Q0 star independently of each other. But after that moment, you use the same Lévy process to drive both Qs. And then you see that you indeed have that Qt and Q0 are correlated, but Qt star and Q0 are independent of each other. And because of that, you have the identity over there. So that is the coupling trick. So you use the same driving Lévy process, and you already feel that that should give variance reduction, right? Well, the estimator that you get then is in, let's say, self-evident notation, something like this. So you sample that Q process, that Q star process, you take this sample mean, and that gives you an estimate for your covariance. And the question is, of course, what can be said about the performance of this estimator? Is it any better than that 1 over r squared that we got? And that turns out to be true. The way to see it is the following. You split the thing that we want to estimate into 4 terms. So here you have r plus plus, r plus minus, r minus plus, r minus minus. And what is different between them? Well, here, empty is the infimum of your xs. So in this case, the busy period that started in, or that was going on at time 0, still did not end. So you're still above the positive axis. You've always been above the positive axis. And the same applies to the star process. So both processes have always been above the axis. So in this case, the busy period of the first one did not end, but of the star process ended. Here it's vice versa, and here both ended. And then there's a crucial observation. If both busy periods have ended, then the Q process and the Q star process are identical. So they are coupled from that point on. They are the same. In other words, that fourth term cancels, and of course it's the one that happens most of the time. Because, well, it's a quite rare thing that busy periods last for a long time. So you let t grow large, and when t grows large, this becomes more and more rare. Or sorry, the other things become more and more rare. This becomes more and more usual. So basically what you see is that the processes Q and Q star go more and more together until they meet when both busy periods have ended. Because of that, we have that the variance that we're interested in is smaller than, of course smaller than the second moment, but also smaller than this object here. We just use the fact that Qt minus Qt star is smaller than Q0 minus Q0 star in absolute value. Remember, one of the terms could cancelled, the other 3 terms remain, and you get something of this type. Well, then you see that things work out well, because here you recognize 3 things that have to do with long busy periods. Here, both busy periods should be long. Here, one of them, and here the other one. So in that sense, it's not surprising that, well, the decay rate of the thing that I wrote over there, which includes the indicator function of a long busy period, has the same decay rate as the busy period itself. So this is for the spectrally positive case, then we call it theta. In the spectrally negative case, we call it Q. But in both cases, you have exponential decay. In other words, we have that the variance is bounded like this. And it means that, well, the width of your confidence interval looks more or less like that. And we see that the number of runs that you need in this case is now 1 over r. So we are back in the old situation where the number of runs that you need is proportional to 1 over the thing that you want to estimate. So it's a substantial improvement, of course. In a rare event probability context, we wouldn't be happy, but in this context, of course, we did way better than the naive thing. But you can use the tricks that I explained for the busy period. So for the busy period, I explained how to simulate efficiently the tail probabilities of the distribution. And with exactly the same change of measure, you can now estimate the R in the coupled algorithm. So you have the coupled algorithm. On top of that, you impose important sampling exactly in the way I described for the busy period case, and you get a logarithmically efficient algorithm. I won't go into details of that. really the same as in the busy period case, but it's nice. So it means that the number of runs that you need with that algorithm is even growing sub-exponentially. So this is really the ultimate thing. Examples. First I look at reflective Brownian motion. So your derive in Lévy process is Brownian motion. I take the standard form. Remember that Q of t looks like this. In the simulation algorithm you have to simulate the value of the Q at time t and at time 0. How do you do that? Well, first, because of Pollack-Kinchen, basically Q0 is exponentially distributed. I mentioned that already. But the interesting thing is that you can very efficiently simulate also the Q at time t. How do you do that? Well, the first thing you do is that you simulate your x of t. X of t is normally distributed with parameters minus t and t. Suppose it has value z, then conditional on that value, we sample that infimum. And you recognize there the Brownian bridge, and it turns out that the distribution function of the Brownian bridge, which is this one, can be inverted. In other words, you can use the standard technique to sample from a distribution using the distribution function. And here you have the form of the thing. In other words, in order to simulate your Q of t, you only have to simulate 3 random numbers. So it's extremely easy in this case. Here a table. I performed 100 million runs per experiment, and the table gives the relative errors, which is the width of the confidence interval divided by the estimator. Well, what you see is that with a naive technique, well, it's horrible. With a coupling technique, it's kind of okay, but with important sampling, you get amazingly low variations. So it works extremely well. You even see that the relative error is growing very, very slowly, so it's more or less constant. Second example, MM1. In that case, the Laplace exponent has that form. You can invert it, you can do all the computations. You can compute the zeta. Remember, the zeta is what you needed in the important sampling algorithm. And here I performed 10 million runs per experiment. And you get the same idea here. You see that again, under important sampling, the relative error is more or less constant. An outlook. What can we do if we make it harder? Well, there are several ways to make it harder. One of them could be to look at Markov modulation. So you don't have a Lévy process that feeds into your queue, but you have a Lévy process that can be in 2 states. So you have a Markov chain, continuous time Markov chain, and in one of the states you use, let's say, phi1, and in the other you use phi2. It's easy to see that the coupling trick does not immediately apply there, because you sample the Q at time 0, but sampling the Q also involves sampling the state of your Markov chain. And when they're in different states, the Q0 and the Q0 star, then it's not clear how to couple them, because, well, they should behave, you cannot use the same Lévy process in that point. But there are ways to get around it. One thing that you could do is that you actually wait until they meet. So you sample under the original distribution for a while until they meet, and from that point on you use the same Lévy process. So that could be a trick, but then you have to know that that happens relatively soon after time 0. It shouldn't be in the order of the busy period. The other thing that you can do is force them to meet. So the Markov chains are in different states at time 0, and you use, let's say, important sampling or so to, well, to kind of speed up the time at which they meet. So one of them has to jump, basically. Well, both ideas could work, but, well, I guess the details are hard, and maybe they don't work, actually. Well, the ultimate goal would be to look at way more complex input processes. So in this case, in the Lévy story, the input process was at IID increments. In this situation, there is something with a very mild dependence, but if you think of fractional Brownian motion, well, what can you do there? It's important to notice that in the fractional Brownian motion case, Q0 and everything that happens after time 0 are highly dependent. So all the coupling ideas that I used there are not applicable. So it's really a completely different setting. So let me end with a couple of conclusions. The first one is that we looked at the analysis of the correlation structure after imposing a reflection map. So we had an input process, we fed it into a queue, which is also called a reflection map. And the question that we ask ourselves is what happens to the correlation structure? So I argued that it's a very hard question for Gaussian inputs, but for the case of Lévy inputs, we could apparently do quite a lot. We had those structural results. Well, that kind of characterizes your function R. We had asymptotics, and we also had efficiency techniques. That's it.